Hi, this is Bob Bosch. I'm going to be speaking on domino steganography. I'm going to prove a theorem. Dracula plus the negative of Dracula equals Frankenstein's monster. Here's a proof. On the left, we see an image that looks like Bela Lugosi playing Dracula. On the right, we see the negative of that image. And if we superimpose them, we get the image in the center, which looks like Frankenstein's monster as played by Boris Karloff. I want to point out that the image on the left is made out of vertically oriented dominoes. The image on the right, the negative of the one on the left, is made out of horizontally oriented dominoes, and the two fit together. If you put one on top of the other, you get the one in the center. And the one in the center is made out of 48 complete sets of double nine dominoes. Now, this project was great fun for me for two reasons. One, I got to work with an amazing collaborator, my brilliant former student, Aaron Kreiner. And also, I got to revisit the project that got me into doing mathematical art, domino mosaicing. Now, I have a book on this subject, and one of the chapters does go into, in great detail, domino mosaicing, how optimization is used to do that. But I want to point out, as I do in the book, that I'm not the person who came up with the idea of using complete sets of dominoes to create recognizable images. That person is Ken Knowlton. I encountered his work back in May 1981 and March 1985, when I was respectively a senior in high school and a senior in college. I came across his work in Omni magazine, in the games column, which was written by Scott Morris. Here we see Ken Knowlton's 24 complete set portrait of his friend Joseph Scala. This was from the May 1981 issue. And then in March 85, we see four complete set portraits, one of Marilyn Monroe, one of Albert Einstein. So really all of the work that I do is done in an attempt that I'm making to be like Ken. I'm emulating Ken Knowlton. So how did Ken Knowlton make domino mosaics? Well, the method that he used, which is also the method that Donald Knuth described in his book, The Stanford Graph Base, I'm going to refer to it as the Knowlton-Knuth method. It is a method that has two phases, two stages. In the first, we partition the image into domino-sized slots, and in the second, we assign dominoes to those slots. Each stage happens to be easy. Each is an instance of what operations research people call the linear assignment problem, and theoretical computer scientists, mathematicians would call this the problem of either finding a minimum cost or a maximum profit, perfect matching in a bipartite graph. This problem is one that can be solved in polynomial time. So let me illustrate it. Here we have an image of Frankenstein's monster as played by Boris Karloff. Whole bunch of pixels. Pixels are grouped into squares. There are 22 rows, 15 columns of squares. Here is what happens when we average the pixels, the grayscale values of the pixels in each square, and convert that and round to 0 through 9 grayscale. So 0 is black, 9 is white. Intermediate values are different shades of gray. So there's the same table of brightness values, grayscale values, and you'll note that I've put a checkerboard pattern on these. And I've done that to highlight the assignment that's actually being done, the linear assignment problem that's being solved in stage 1 of the Knowlton-Knuth method. What we're doing is assigning white squares to neighboring dark squares. When we assign or pair up with a white square with a neighboring dark square, we're getting a domino-sized region. So we want to either minimize some cost function or maximize some profit function. Here we're going to maximize the total contrast score. So we see what results from doing that. And again, this is solved very quickly. To give you a sense of what the contrast scores are, let's take a look at the lower left-hand corner. The dark square 8 and the light square 4 end up being joined together. They belong to the same domino-sized slot. And the contrast for that would be 4, 8 minus 4. And in the lower right corner, we've got a light square 8 and a dark square 2 that belong to the same slot. they were paired together, the contrast score for that slot would be 8 minus 2, 6. So this partitioning of these squares into domino-sized slots maximizes the sum of all these individual contrast scores. And we can then try to assign actual dominoes to it. And when we do, we get something that's recognizable. And the errors that we make here aren't that big. If we look at the lower left-hand corner, for this 8-4 slot, well, an 8-4 domino ended up going on top of it. So the cost of that is clearly 0. What about this 8-2 slot in the lower right corner? Well, a 9-2 domino went on top of that. The cost of that, how could we compute that? Well, we could take the quantity 9 minus 8 squared plus the quantity 2 minus 2 squared, get a cost of 1. So what I'm pointing out here is that we don't need to solve that first stage optimally to get something recognizable. The picture on the left shows the optimal solution to phase 2 if you use purely vertical slots. The image on the right shows the optimal solution to phase 2, stage 2, if we use mostly horizontal slots, vertical slots in the rightmost column. Remember, there's an odd number of columns here, so we can't use all horizontals. This shows all 3 of those portraits, all 3 domino portraits. The one on the left, I think, looks best, and it had the best second stage cost. 97 was the measure of the total error, dominoes versus the numbers that lie underneath. The purely vertical one is a lot worse in terms of that second stage cost, 305 compared to 97, and the mostly horizontal one is even worse. But again, the main point here is that we don't have to do the first stage, the first phase, optimally to get something recognizable. And this is what allows us to do domino steganography. So here what we see is 2 portraits of Frankenstein's monster played by Boris Karloff. Each is made out of 48 complete sets of double 9 dominoes. What I want us to imagine here is that we've made these out of real dominoes and that we have glued down the dominoes onto a board that's pure white. And then also, when we glued them down, we actually glued down the vertical ones, the dominoes that are oriented vertically, we glued them down quite well. And in fact, we forgot to glue down any of the horizontals. So I want to ask us what's going to happen if we were to allow this board to tilt forward and all the horizontal dominoes would fall off because they weren't glued down. This is what we end up with. So it turns out that in the left image, what was hidden beneath was this image of Dracula played by Bela Lugosi. And in the right image, what was hidden beneath was this image of the Mummy played by Boris Karloff. Now, both of these hidden images are made entirely of vertical dominoes. So how do we do this? Well, we imagine that we have an unlimited supply of white dominoes. We have an unlimited supply of black dominoes, and we're going to do the best that we can to use them to construct an approximation of some target image. And we're going to just impose a very strange rule on how we place the dominoes. When we place the black ones down, we have to place them down vertically. When we place the white ones down, we have to place them horizontally. So blacks have to be used vertically, whites have to be used horizontally. And that's what's responsible for this. So ultimately, what we're going to do in phase 1 is, figure out a slot pattern that in itself, vertical, horizontal, defines some hidden picture. And then once we have that slot pattern, we're going to assign dominoes to it to give us the primary picture. The math behind it involves 2 sets of variables, V's and H's. Vij is 1 if we place a vertical domino with its top square covering the row I, column J square of the board. Hij is a similar sort of variable for horizontal dominoes. Hij is going to be 1 if we place a horizontal domino, a white domino, horizontally with its leftmost square covering square ij of the board. Now, these are the 4 ways that cell ij can end up being covered. There's 2 ways it could be covered vertically. There's 2 ways it could be covered horizontally. Precisely one of those 4 ways has to be used for every single square of the board. So we need these linear equations. For each cell ij, we need the sum of these four things to be 1. Now we also need one more set of variables so that we can keep track of how bright cell ij is. Zij is going to be the color of cell ij, 0 if it's black, 1 if it's white, and it's relatively easy to show that Zij is the sum of hij-1 and hij. I'm not going to go through the details. The objective function is the we're going to minimize the sum of all what I call 2x2 errors. The z's tell us how bright dominoes are, the betas tell us how bright the underlying image is. So here's a 3-set version of Frankenstein's monster. Here's the top left corner of it. In the top left corner, we see which dominoes are vertical in black and which dominoes are horizontal in white. And in gray, we also see the betas, the brightness values of the squares that are in the target image that we're trying to approximate. Now, in this expression that you see above, the sum of the zij's would be the sum of here 0, 1, 0, 1, black, white, and then the sum of the betas would be what we see here. So the sum of the z's gives us how bright the domino portrait is in this section, and this tells us how bright the corresponding region of the target image is. And we want the difference between the two to be small in magnitude, so we're going to minimize the square of the difference. Now we're going to do that not just for this 2x2 region, but for all 2x2 regions. Here's the second of them. The dominoes here for that 2x2 region are horizontal, so they're white, so we get 4 1s, and the betas end up being what you see here. All right, I'll leave you with just some of my favorite quotes from Stravinsky, from Heller, paraphrasing T.S. Eliot. These are quotes about the value of constraints. I like working with constraints. And if you enjoyed this, feel free to contact me. This is my website. Check out my Twitter or check out my book. All right, take care.